Thank you very much. So I want to continue this theme that I was developing in the last couple of lectures. So, of course, I'm heading towards the concept of the dynamical zeta function, but since not everybody is so inclined towards such things, I was trying to build up some sort of motivation and framework for this. So in the first lecture, I talked about the Riemann zeta function and its application to the prime number theorem, very classical, going back over many years, several centuries. And as a sort of prelude to the stuff on geometry, I talked about the case of graphs and counting loops in there, and the associated zeta function in that case, which is the Ihara zeta function, which is, if not simple, at least it's relatively straightforward to understand. In the last lecture, which was yesterday, I was talking about the geometric analogue of that, and a lot of these ideas have parallels. So if you think of loops in a graph, they're very similar to closed geodesics on a surface, at least philosophically. Mathematically, you're required to do a bit more, but in principle, if you understand one setting, it's easy to guess what happens in the next, and so kind of extrapolate. So the reason I haven't written anything here is because you can forget it. It's just in the past. We're moving on. And so yesterday we talked about surfaces, and perhaps we could have talked about manifolds, but we just talked about surfaces, compact surfaces and non-compact surfaces. And in that case, we were counting closed geodesics, just loops of locally the shortest distance on the surface. And the associated complex function was the Selberg zeta function. And that was the guy that carries all the information about the countable set of lengths that we have. And then from that, you could derive the prime geodesic theorem, which tells us that if you count geodesics, irrespective of whatever surface you use, you get the same asymptotics. So the fine structure of the actual lengths is different, but globally it kind of looks the same because this growth rate, this asymptotic, is independent of any of the geometry, which is kind of amusing. And so in this lecture, I want to progress on to the final part of the lectures, which is the dynamical part. And in fact, of course, it inherits stuff from the previous lectures, because when we were talking about geodesics on a surface, of course, we could have thought of that dynamically by looking at the geodesic flow. It's a well-defined flow. It's parameterized by the real numbers. And it's an example of a more general class of flows I will define in a moment, the Anosov flows. And the closed geodesics, well, in that case, they would have corresponded to closed orbits for the geodesic flow. And the Selberg zeta function, well, we can replace it by a more general object where the lengths of closed geodesics are replaced by, more generally, the periods of closed orbits for these flows. And so there's a natural parallel between these things, and it comes out also that there's an analogue of the prime geodesic theorem where you probably guess, instead of counting geodesics, you count closed orbits for the flow. And in that case, instead of looking at the length, you look at the period. So this is what we did yesterday, and this is what I plan to do today. And of course, there's also some subtext down here about the Riemann hypothesis, which I'll also mention in passing. There is a more fundamental comment I should make that's in the background, so it's easy for you to forget about it, so it's not very important. But the techniques that were used in proving the Selberg zeta function are basically harmonic analysis. They're related to homogeneous spaces. They work for constant curvature. So they're great in that context. And the dynamical viewpoint's power is that it works more generally. It works for variable curvature. It uses less analysis in the sense of classical harmonic analysis or non-commutative harmonic analysis. However these things were proved, it uses more dynamical ideas. It makes it more flexible. But by the same token, you can't always prove quite so much. You can't get very good error terms, for example, in these asymptotics. So it's a different point of view, and it works in a broader context somewhat, but it doesn't always necessarily give you the same strength of results. And the other thing I was going to mention, just in the passing comment, was that when I talked about the special case of an infinite area surface, I mentioned this rather complicated construction where you introduce these Ruel transfer operators. This is a kind of technology which was very useful in the context of dynamical systems over many years, but in the present case it's now been kind of supplanted to some extent by other techniques, which I'll try to say a bit about. Anyway, so that was just some me rambling a little at the beginning of the lecture to set the scene. You can forget everything and I'll just start as it should go. So this is going to be, I think it's 6, and this is the Ruel zeta function. For Anosov flows. There are other kinds of zeta functions attributed to Ruel. There are zeta functions for diffeomorphisms, not just for flows, which I could talk about, but then the problem is that I lose the coherence of the lectures, so I will skip them. There is a discussion of them in the notes, and they play an important role, but for the moment I just want to concentrate on flows. So I'll let phi of t be a flow. So this is going to be a C infinity flow on a compact manifold. So t here is just time, and it does all the things you want of a flow. It's just a family of diffeomorphisms with the property that when you flow for a certain time and flow for another time, then you just sum the times and you get the corresponding diffeomorphism. Okay, and then the definition of the Anosov flow is the following. So we call the flow of this form Anosov if the following are true. So it's got a fairly complicated definition, so let me just state it and then explain it. So first of all, if you look at the derivative on the manifold, then there exists a splitting of the tangent bundle so into 3 bits, which I'll call E0, ES, and EU. And these 3 bits are of the following type. First of all, E0 is one-dimensional, and it's in the direction of the flow. And secondly, we can find constants c and lambda, which are positive, such that if you look at the derivative of the flow restricted to the bundle ES, which stands for the stable bundle, then this contracts like e to the minus lambda of t. And if you look at the derivative restricted to the unstable bundle and you flow backwards in time, then this contracts like c e to the minus lambda of t. And I'll make a second assumption to make life easier, which is I will assume that the flow is transitive. And then I'll explain what all these things mean. Well, transitive is easy to explain. It just means that there exists a point in the manifold such that the orbit is dense. So the union t is an element of R, phi t of x, contained in M, is dense. So I'll just take that for granted. What do these other conditions mean? Well, what it means basically is the following, that if you take a point and you look at its orbit under the flow, so this might be a point, let me call it y so I don't keep using x all the time, and you flow to a point to t of y, then the tangent bundle tells you what happens transverse, well, it tells you what happens locally. So in particular, there'll be some direction which will correspond to the stable direction, such that in that direction things get closer. And there'll be another direction which is corresponding to the unstable bundle, which is over here. And in this direction things expand, or in fact they contract going backwards. So the picture should look something a bit like that. So this is an example of a uniformly hyperbolic flow, and what really happens is that as you flow forwards in time on the manifold, then if you look in the flow direction, of course nothing much happens, you just get translated. But transverse to that, what happens is that in one direction things get squished, they get contracted in, and in the other direction they get expanded out. So this is a characteristic behavior of these kinds of flows. And they were studied by Anosov in the 1960s in particular. And why are they interesting? Well, because one of the main examples, perhaps the main example, is precisely a geodesic flow on a manifold or surface of negative curvature. So the main example is a geodesic flow on a compact manifold of negative curvature. So since this is kind of a fundamental point, let me just do it in a little detail. So here's an example, and it's the geodesic flow. So this is a geodesic flow on a surface of negative curvature. Okay, so let me draw such a surface. Here it is. Just like it was in the previous lecture, this is a surface V, and we're assuming that the curvature is negative. Before I assumed that the curvature was equal to -1, but I now allow myself the luxury that it might be just negative. It has to be bounded away from 0 by continuity and the fact that the surface is compact. And then in this definition, M is not equal to the surface, but it's actually equal to tangent vectors to the surface, which have unit length. So the manifold itself consists not of the two-dimensional surface, but the three-dimensional space consisting of points in the surface and a one-parameter family of directions. So this is what V is going to be. And so the flow is meant to take us from unit tangent vectors to unit tangent vectors. So it's meant to take us from M to M. And the way it's defined is kind of easy. So we take our vector V, which is this guy, and then we define it to be at time t, well, I'll say it's this quantity. And what's this? Well, this is where gamma of V from R to R, no, it's into M in fact, no, it's not even into M, it's into V, is the unit speed geodesic with initial conditions at time 0 equal to V. So what you should have in mind is that V is a starting point for this geodesic, and at time 0 we start at this point facing this direction and we give it a push, and then the geodesic is going to be a curve on the surface. Maybe it doesn't want to be green particularly, so whatever colours I have at my disposal. Maybe purple's nice. So there'll be a geodesic which at time 0 goes through this point in this direction and maybe gets to here. So this is going to be my geodesic gamma V of something. Let's put S there. Maybe U is better. And then when I get to this point at time t, which is gamma V of t, then the derivative, the direction, is given by this. So it's just pushing the unit tangent vectors along geodesics, and that's the definition of the geodesic flow. And this particular example, because of the negative curvature, has the property that this is true, that there are directions in which things expand and directions in which they contract. It's not so easy to see in the picture, but in fact EU and ES correspond to stable, maybe unstable that way around, unstable and stable horocycles. But that's just a comment. If you are not very familiar with horocycles, don't worry about it. It doesn't play any particular role. The only important thing is that this example of a geodesic flow is one of the canonical examples of an Anosov flow, and the Anosov flow is the correct setting for the dynamics I want to describe. So if you were happy before with geodesics on surfaces, we haven't really advanced very much because the main example will still be associated to these surfaces, but the correct formalism would be to define it like this. So I put this in for completeness. Okay, so let me try to develop this analogy which I was commenting on the left board, which is where we want to go from the geometric viewpoint to the case of a dynamical viewpoint, which means that we want to go from the geometry of these geodesics to the flow. And so we need to talk about these things. So this will be the next point. To get the zeta function, I haven't got there quite yet, we need to look at closed orbits and the Ruel zeta function. Okay, so I use the following notation. We call tau a closed orbit of prime period lambda of tau. So this is just going to be some positive number. If it does the obvious thing, well, if in fact for any point x on the orbit, we come back there in a time lambda of tau. If we have that phi at time lambda of tau of our point is back to the same place. It's not very complicated. And here we choose lambda of tau chosen to be the least such value to be the least. So if we think of our Anosov flow as being something happening on some vague manifold rather than this concrete example, then a closed orbit is what you think. It's something which is closed and it's an orbit. So in particular, it's denoted by tau, and some point will come back to the same place after time lambda of tau. And because of the hyperbolicity, there are only countably many such guys. And so I use the following notation. We can denote pi of t, some piety in this. So t is positive, to be the number of such closed orbits such that lambda of tau is less than t. And again, as I just said, this is going to be finite for any finite t, and the reason is that it's due to the hyperbolicity, well, due to the definition of an Anosov flow. As you can see in the picture I drew, things have a tendency to spread out in different directions, and so it's very difficult for closed orbits to stay close to each other. They get pushed away, and that's what stops them from having too many orbits of the same sort of length. And we're back to the same problem, which is we take the real line and we put little benchmarks on it corresponding to different lengths. And this is just asking how many we can find up to a length t. And it's completely analogous to the previous counting questions. A useful quantity to introduce here is the following. So let me state this as a lemma, which I will attribute to Sinai from 1966. And what it says is that the limit as t tends to infinity of 1 over t, the log of pi of t, exists. So we have a function, it's monotone increasing, it grows in fact at an exponential rate, and it's a sort of pure exponential rate in the sense that this limit exists as t tends to infinity. And I'll denote the limit by h. And this is called the topological entropy. Entropy of the flow. Like all good things in mathematics and in ergodic theory in particular, there are lots of definitions of entropy, and this just happens to be the most convenient for my purposes. If you've seen other definitions, which I'm sure you have, then they may be different, but in fact it's kind of convenient to use this one for what I'm going to say. And it works in the context of anosov flows. It doesn't work quite so well for non-hyperbolic flows. And why is entropy relevant here? Well, you could think of this as being like some sort of normalization. Let's say that it sort of replaces the normalization by, say, curvature, by area or curvature for geodesic flows. So if you take a flow, an anosov flow, and you mess around with it, you speed it up, you do something to it, then you'll get different values of h. But we're interested in a specific characteristic value for this given flow. So it plays a role there. Anyway, let me just move over that by saying that we can now define the zeta function, the Ruel zeta function, one of many Ruel zeta functions, but the one most relevant to what I want to say. And the definition is almost exactly the same as for the Riemann zeta function. So the Ruel zeta function is defined by, well, I define it like I have all the previous ones as a Euler product. So it's a function of a complex variable, which I'll call C. And in the great tradition of at least the previous lectures, I'll use zeta for almost everything. It looks like a zeta function. But in this context, it's the Ruel one. It's the product over all the possible closed orbits, of which there are countably many. And then it's the product 1 minus e to the minus s lambda of tau to the minus 1. So we take a product over the countable set of closed orbits. For each closed orbit, we have a number, which is the least period, which appears here. And then we multiply it by our complex variable, take this infinite product, and Bob's your uncle, you get this guy. And in the case of the Riemann zeta function, we knew it converged on a half plane, as did the Selberg. And in this case, the half plane is providing the real part of S is bigger than h, the number we defined up there. So that's the role of h in this. It gives you some sort of, if you like, normalization of these flows. And let me make two remarks to try to connect it with what happened before. So the first remark is that this is a definition which is closer, which is closer than the Selberg zeta function definition to the original Riemann zeta function, which is closer in some sense to the definition of the Riemann zeta function. zeta function, which you recall was given by zeta of s was a product over primes, 1 minus p to the minus s to the minus 1. And the reason is because if you use the correspondence, that instead of primes, you associate closed orbits. And every time you see a value p in this definition, you replace it by e to the e to the h times the length of tau. So using that correspondence, you just get, by substituting for every p one of these guys, you get precisely this definition. So it's kind of motivated in that sort of way. And secondly, there is a connection with the Selberg zeta function, and so we can relate it to the definition of the Selberg zeta function, which had a slightly different definition for historical reasons, and the way it's defined is probably the following. Zeta of s, I've written, is the same as the Selberg zeta function at s plus 1 divided by zeta of s, or alternatively, if you want to write down the Selberg zeta function, it might be the same as the product n equals 0 to infinity of zeta to the s plus n to the minus 1. So formally that's obvious, and in fact if you have extensions then it's easy to check. So if you were worried about the connection between these zeta functions, this is meant to clarify it. If you weren't worried, feel free to ignore it. Hi.
Question?
Sure.
In the C9's lemma, the limit is positive and finite?
Yes, indeed. The limit here in this case is indeed positive and finite. Let me write it's in 0 infinity. Yeah, the positivity is a consequence of this hyperbolicity of the stretching. And the finiteness, I guess, is probably for the same reason. Yes?
I don't see the h in the definition of...
Yeah, so let me eradicate the h from here. So if I put the h in, it would have the effect that it would translate the pole to be at s equals 1. But I think since I'm talking about how the zeta functions are written, I should eliminate the h. Thank you very much. I should be aware of these things. Okay. So we have our flow. We've got countably many orbits. They grow at some prescribed finite bounded exponential rate, which puts us in good shape. And then we can define the zeta function in this appropriate way. And as I just said to Karma, if we had put the h in here, then of course it would translate this back to 1. But let me not do that because it would just confuse matters. Okay, so it's a zeta function. We've defined it. What are we going to do with it? Well, we'd like to apply it to understand maybe the closed orbits, but in order to do that, we've learned that we need to study its complex behavior. We have to know where it has an extension, where it converges, and such things. And so let me just say something about that. There'll be a slight interlude while I look for the board rubber, which is here. And so a lot of the results that I've mentioned before are just going to look rather similar. This particular zeta function is going to converge on a half plane. It's going to have various kinds of extension properties, and then we're going to deduce from that some asymptotic results. So these are going to be the basic properties of the Ruel zeta function. Okay. In order to make life easier, I'm going to make a generic assumption. It makes life easier because it means I only have one statement rather than two. So let us make the following simplifying assumption. And the simplifying assumption is that we can't find a real number A with the property that if we look at all the lengths the least periods of closed orbits, where tau is a closed orbit. So this is a bunch of numbers, and we want to say that they're not all contained in A times Z plus somewhere, maybe plus. So maybe even N would be better for the natural numbers. So that just says that, i.e., lengths, no, periods are not multiples of a single constant A greater than 0. So I want to make this simplifying assumption, and two comments are that it's true, it's always true for geodesic flows. Secondly, that it's generically true in the bare sense. There's a dense G delta of things that have this property, possibly even open. And a third comment is that without it, it's even easier. Without it, the theorem will be easier, but different. Okay, so this is just to make my life slightly easier. And the theorem is, again, a theorem about the domain of the zeta function.
Easier to state or easier to prove?
Easier to prove. So the statement will be slightly different, prove. But in fact, if I did assume this condition that they're all multiples, it makes the proof much easier of a different statement. So first of all, zeta of S, let me actually put the precursor down. Let's say that zeta of S converges to a non-zero analytic function for the real part of S greater than H. So in the case of geodesic flows and the Riemann zeta function, it was more natural to take 1. But here we don't have a natural value except for the entropy, and so we use that instead. And let me draw a picture just to illuminate this statement. And the picture is going to be the usual one. So here's the complex plane. Here is 0. Here is H. And all I'm saying is that it converges on this plane, half plane, to an analytic non-zero function. Secondly, firstly, I suppose, since I haven't numbered them yet, zeta of S has a meromorphic extension to the entire complex plane. So in fact, you can extend it as a meromorphic function, which means it's analytic, but it might have some isolated poles thrown in. So this is where it's analytic. And this is where there is a meromorphic extension. And within this extension, we can say that zeta of S has a simple pole at S equals H. So this is a simple pole at this value. And thirdly, that there are no more poles or zeros on the same line. So no more zeros or poles on the line, the real part of S is equal to H. If I did not make this assumption, then it's the third one that fails. But it fails in a way which is easier to adapt. So this part corresponds to this condition. Otherwise, it's still true. So all that says on this line, we don't find any other zeros or poles. Okay, and the attribution for these results is the following. So part 1 was proved rather recently by Giletti, Liverani, and myself, and it's yet to appear. Part 2 was proved by Ruel in 1978. He proved that from this domain, where it just converges to an analytic non-zero function, you could push the extension to a neighborhood of H. And he told me that it was a completely useless result, so he included it as an exercise in his book. It's exercise 7b, I think, in his book called Thermodynamic Formalism. And there's a long, tortuous story I've included in the notes about how Bill Perry and I couldn't solve this exercise, and we wrote to Ruel and stuff. Very embarrassing. Well, not really. It happens. And the third part was proved by the great Bill Perry and myself in 1983. And as in all of these things, if you prove something about the zeta function, any zeta function in any context, the more you prove, the more you know. And as a corollary, we get an asymptotic counting result. So as a corollary, we get the following basic result. Following the footsteps of Hadamard, except he didn't study Anossov flows. So this is a theorem, the prime orbit theorem. I didn't say what this condition was called. It's actually called the weak mixing condition. Doesn't really matter because I won't use it again, but just in case you were curious. And it says that under the above hypotheses, that is that we have a C infinity flow. It happens to be a Nosov, and it actually satisfies this condition as well. We get that pi of t, which is probably disappeared on the board, but it was just the number of orbits tau, such that the least period was less than t. So that's what it was. Well, it's actually asymptotic to e to the ht over ht as t tends to infinity. And let me just make a remark, which is for the prime geodesic theorem, you have that there's a bijection between closed orbits for the geodesic flow and closed geodesics. And in this particular case, the entropy was equal to 1, since in that case we assume that the curvature was equal to -1. So some calculation tells you that the h is equal to 1, so you're in luck. It gives you the same statement as you had before. One doesn't need to panic about the fact that it looks different because there's an h there. Okay, so in fact this can be thought of as an extension of the theorem for counting geodesics. It works in two different ways as its generalization. First of all, it works for variable curvature, which is good, and it also works for these more general Anossov flows, but since I've only given you one example, that might not be so exciting. Okay, so is there an analog of the Riemann hypothesis? Is it possible to say, well, we don't find anything else like zeros or poles in some neighborhood like this? That would be the next question, and let me attempt to address that. So the next point is to look for an analog of the Riemann hypothesis. The goal of that being maybe to say more about the error terms in counting of closed orbits, in the same way that we look for error terms in counting prime numbers in number theory or in counting closed geodesics in the geometric analogue. And so next section would be analogue of the Riemann hypothesis. I didn't write down at the beginning what my plan was for this lecture. What I'll do is I'll talk about the analogue of the Riemann hypothesis, then I'll say a little about the proof after I've talked about this, and then if I have time I'll finish with something slightly different. So this is my plan. So there should be 2 more sections on this, and then I'll try to finish on something else. Okay, so let's talk about this other property that we're looking for on the domain of the complex function, the Ruel zeta function. And the idea is that we want to get an extension, but we have to make some additional assumptions. So we can only get a stronger result like an analogue of the Riemann hypothesis under some more assumptions. Okay, so the assumptions tend to be fairly technical about contact flows, so I'll restrict just to the case of geodesic flows. So let's consider a geodesic flow on a compact manifold, and rather than just a surface, I'll assume it may have higher dimension. So the corresponding technical condition to make it an Nosov is that it should have negative sectional curvatures. So let's assume we're looking just at geodesic flows on such manifolds. So they're all examples of Nosov flows. And our extra assumptions in this context are the following. Well, there's 2 possibilities. We could assume that we have a surface. So we could assume that either the underlying surface was a surface. The underlying manifold was a surface. So V is a surface, which means that the unit tangent bundle would have dimension 3. So the dimension of M would be equal to 3. I have to resist the temptation to put an H after dimension, to put meaning Hausdorff dimension, which tends to come up in other lectures. I'll assume either I'm on a surface, which is in fact the only case I really talked about before, or if I'm in higher dimensions, I'll have to assume that V has a pinching condition on the curvature. So I could assume that the dimension of the surface manifold is greater than or equal to 3, and the sectional curvatures, which I'll just denote by kappa, are pinched between -1 and -1/9. So this is a 1/9 pinching condition on sectional curvatures. So if you take a manifold in higher dimension, which has all the sectional curvatures equal to -1, which you would get if you started from the case of simply n-dimensional hyperbolic space, and you perturbed it a little, then this condition will be true. It's just saying you're close to constant curvature in a quantifiable way. So these are all technical conditions, but under these technical conditions we get a result, and the result is the obvious theorem. So this is the analogue of the Riemann hypothesis Riemann hypothesis. And it says there exists, so under the above, under either of the above assumptions, well, we have that there exists an epsilon greater than 0, which is going to be the width of this strip, with the property that such that the zeta function, zeta of s, the Roelle zeta function, has no zeros or poles in the region. The real part of S is smaller than h and bigger than h minus epsilon. So a kind of weak analog of the Riemann hypothesis is true, so nothing extra happens in terms of poles and zeros in this particular band, this strip. Epsilon is not so easy to quantify, which is why we don't say anything about it. The first statement, in fact, is quite old. It's due to Dima-Dolgo-Piat in some form, and in fact it was implemented, if you like, by myself and Richard Sharp, but the basic idea is due to Dima from 1998. Dolgo-Piat, was a Y missing. Piat. And the second statement is due to the three of us again. This one. This is Giletti, Liverani, and myself from the same paper. So you get some sort of weak version of the Riemann hypothesis under some sort of technical conditions. And you might reasonably ask is, if you just assumed this condition, would it be true that you always got this without all these hypotheses? And the answer is nobody knows. There are no counterexamples, and there's no convincing argument why it shouldn't be true in general. Well, relatively general. And why would we care about this condition? Well, for exactly the same reason that people might care about the Riemann hypothesis, because it gives you better counting estimates. It gives you error terms. It gives you error terms on this particular function. So as a consequence of this, we get that under the same hypothesis, which means for a geodesic flow on a manifold with these certain conditions, we have as a corollary under the above hypotheses, well, one of the two hypotheses, we have that pi of t. My t's are looking like tau, so that's meant to be a t. That's also a t. This counting function, well, it's actually got a more explicit or accurate form. It's actually some standard function, which is the integral from 2 to e to the ht du over log u, which is a standard function called LI-EHT. So h is again the entropy for the flow, and it's equal to this up to some exponentially smaller estimate e to the minus epsilon t. The epsilon here again, I should take slightly smaller than the epsilon there to mess around with the analysis, but immorally it's just this. So it gives you a sharper estimate on these counting functions. And there's a long history of counting closed orbits for anosov flows and closed geodesics in general, dating back to Selberg and the last lecture and the results I mentioned there, and the great Margulis, who proved these things also in the 60s, I guess. Okay, I haven't left these people out for lack of reverence. It was simply because of time more than anything. But I'll try to put more in the notes. Okay, so let me try and say a little about how you construct the meromorphic extension of the zeta function to the entire complex plane, just working from the original definition. And what I want to do is just state the bare ideas without any details at all, because it's more of a kind of philosophical sea change rather than a technical triumph to get these things to work. So in the previous lecture, when I talked about the zeta function for infinite area surfaces, I introduced a transfer operator, which was kind of a classical transfer operator, which involves summing over orbits of things, where you got lots of things in your summation. But in fact, the modern approach, if you like, is slightly different. And so I'll discuss that. So this is constructing the Meromorphic extension. Of the Ruel zeta function. So just the ideas rather than any sort of detail. So basically we need to start off by introducing some operators again. Operators always do the job here. So we need to introduce families of operators. Juice of, families of operators. I'm trying to get the grammar right, which is proving more complicated than the mathematics. Okay, so here's the first point. So let's say that we start with a space of functions. It's a perfectly decent Banach space. It's not the one we're going to use, but it's a space defined on our manifold. And we can define an operator which maps us from continuous functions on the manifold to itself. And this operator I'll denote by L using a time-honored convention. And it'll be a family because I'll put a T at the bottom. And this T here is just going to be some real parameter which is positive. And how is it defined? Well, it's defined in a rather unexciting way, quite popular in ergodic theory, is that I will take my function at a point x, and I will define it to be just pushing the flow forwards or backwards. I always get confused about which way, and then composing it with this. Something which ergodic theorists have been doing for many, 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 many years. So I remind you in this notation, phi of t from m onto m is just the Anosov flow. So that's a starting point. It's not necessarily a very auspicious one. But we can now step up a bit. So we want to get a complex variable in, because we're looking at zeta functions of complex variables. And so we can associate for each complex variable S in C a resolvent operator, which I'll just describe as another operator. And this will depend on S, and so I'll call it R of S. And this, well, let's keep on the same space, not that it will be there for much longer. So continuous functions on the manifold to itself. And the way we do that is we take, again, our function W, which is just a function on the manifold. And so we write down the new function at a point x. I guess I should have set up here that x was now a point of my manifold. And the way we do it is just integrating. So we integrate from 0 to infinity of e to the minus s t lt w of x dt. Okay. And so this makes some sort of sense, providing, I guess, the real part of s is bigger than 0, something like that. So it gives me an operator which now depends on values of s. And I could, of course, skipped a step by putting the L of t down here, but I wanted to try to make it look fairly transparent. Okay, so in the previous results, operators appeared and they had good spectra. They didn't have complicated spectra. They had like isolated eigenvalues and stuff like that. particularly if they're matrices, or trace class. And the difficulty with the continuous functions is that they don't have that property. It's too big a space, and so these operators have kind of big spectra, too many eigenvalues. So in fact, you need to replace this rather old-fashioned space C0 of M by a better Banach space. And so for which R of S has less spectrum. And these are what are called anisotropic spaces. Anisotropic. And these are spaces which are actually not spaces of functions, they're actually spaces of distributions, which are more generalized than functions. And they can be constructed in different ways. And in some cases, they are constructed by hand. You sit down and you look at the definition of the Anosov flow, and you look at little pieces of stable, unstable manifold, and you mess around a lot, and you construct these spaces. Or you can do it using more analysis, like sort of harmonic analysis, using more sophisticated techniques. Either way round, these spaces are built with the property that these operators have got better spectrum. And when you have this property, you're in much better shape. And so once you've done that, we then convert the spectral properties of these families of operators to properties of the zeta function, because morally you want to write, you want to use some notion that we're going to write the determinant of I minus R of S. Let me put all of this in quotation marks. This is going to be like the exponential of, I think there's a minus sign I keep missing, n equals 1 to infinity, 1 over n, the trace of R n of S. Something like that. You've got to make sense of all of this, so you need good operators for which you can make sense of the trace, whatever that means, and also of the determinant. And this means that we can say something about some complex variable. S is still going to be in C, but it's not quite the zeta function. We have to do something else, and so finally, to get results on zeta functions, to get the final results on zeta of S, you have to repeat the construction using not a space generalizing functions, but a space generalizing forms, using differential forms. So this is not meant to be very illuminating, it's just simply meant to tell you the philosophy. There's no details of proof in this at all. I should remark that I was checking my email to see how long it took us to prove this result, and the proof of myself, Giletti, Liverani, and myself took from 2007 to 2013. I'd like to think it's because we were working on other things in between, but perhaps it wasn't. And there's now another proof, as of last Wednesday, which is due to, I have to look up the spelling, DYATLOV and Zworsky, which appeared on the archive on last Wednesday. So they have a proof. Also, it's philosophically rather similar, but uses more clever analysis. What else can I say that's useful? Probably not so much. Okay, so this is just a kind of technical description of what's happened. And the main philosophy here is in the old days when people used transfer operator techniques, there was a lot of messing around with the dynamics to put it into the right context. But the brilliant idea here is just to push forward with the flow and change the Banach space. That makes life much easier. Give or take 6 years of slogging through the details. Okay, so looking at my notes, I had a list of problems which I was going to bore you with, but I think instead I prefer to finish on a slightly different topic. So if you'll forgive me, I will do that. I'll also have to move the board rubber, I think, before it gets crushed. If I put my hand underneath, I suspect it suffers a similar fate. Okay, so just to finish off, I'll talk about another topic to kind of raise the tone a little. And so earlier on in the course, and also in Mike's course, he talked about the Artin-Maser zeta function. And the name of Maser is going to be now invoked again. So I want to talk about a recent application of these ideas. These ideas means the classical stuff, not the stuff I just wrote on the board. And this is related to work of Barry Maser, Kurt McMullen, semicolon maybe, and it's related to knots. Okay, and so the story is the following. I'm on sabbatical this year, and so before Christmas, and in fact until February, I was in Paris. Well, not actually in Paris, it sounds better to say I was in Paris. I was actually in Bieux-sur-Yvette, just outside Paris, and during November I got lots of correspondence with Kurt McMullen, who was asking me questions about zeta functions and counting stuff. And it was in connection with the following objects, so let me just set it up. So let's assume that M is now a compact three-dimensional manifold. Compact three-dimensional manifold. And let's assume that we have a sequence, an infinite sequence Kn of n equals 1 to infinity of be a sequence of pairwise disjoint one-dimensional, well, let me just say embedded circles. So we have our three-dimensional manifold, and we have lots of curves indexed from 1 to infinity. So here is K1. I won't draw them the same color. Here is maybe K2. And here is K3, etc. And there's a following definition, which is due to Maser. And it says the following. We say that the sequence Kn, 1 to infinity, is equidistributed. In fact, he calls it Chebatarov equidistributed, but since I can't spell Chebatarov, I'll just write equidistributed. If for any n greater than or equal to 1, if you just look at the first n of these loops, you have the property that if you look at a character, so this is a character from the fundamental group of the manifold minus these loops, the first n of them, so that's n equals 1 up to uppercase n, so finitely many are taken out. So the character is just some nice map from this group into G, which is just going to be a finite group. Then the equidistribution condition is the following. So if at any n greater than and C contained in G being a conjugacy class, then you have the property that the limit as, I've used up n, so it's going to be uppercase M. Oh, M is bad because I've already used that. L maybe. Haven't used L probably. So L tends to infinity of the number of those guys between n and this limit L, with the property that the character of the element of the fundamental group containing the next guy in this sequence is an element of C. Well, you wanted that this thing divided by, I guess, L minus n, but L will be okay because it's a limit, should be equal to the number of guys in C over the number of guys in G. So it's kind of complicated looking statement, but what it's saying is that you've got this infinite sequence of loops. You stop at some stage, and that just gives you a finite collection of loops. You take them out of the manifold, it gives you more sort of holes in it, and then you look at the fundamental group of that. This is
look at that for all groups G.
yes. So this should be for any for any finite group. So you at the beginning, if I put the quantifiers in the right order, I should have said that for any group, any finite group, and any character into that finite group, you have this property. So you've got the manifold. You take out a finite collection of these guys. Could be as many as you want. So it gives you a manifold that seems to have more gaps in it than before. So the fundamental group may be kind of more complicated. It's probably infinite anyway. And then, in order to get something finite, you look at the images under some character into G. And then you ask, well, how are these images distributed when you look at the images of the other guys in the sequence? You keep on going up. And these are going to weave in between and out of all these other closed geodesics, and how they're distributed is described by this. So the character, the finite group, are just here to make it more concise, but it's really an equidistribution result on how different of these circles, these loops, are distributed relative to all the previous guys, in some sense. Anyway, this was some definition due to Mesa. And for those of you that are interested in things like equidistribution results in number theory, then it's a bit like Chebotarev's theorem, which is related to how things split in different number fields. Those of you who don't like number theory so much, well, everybody likes number theory. There's no point saying that. Okay, so this is just a definition. It's just saying that, you've got infinitely many circles, and under some circumstances, they're kind of nicely distributed in some definition that makes sense. And the result that Kurt was trying to prove, or one of them, was the following theorem. And so this is due to Kurt McMullen. And it's on his webpage if you like checking these things out. So it's also from, maybe it's 2012 or 13, I'm not quite sure which. And it says if you have the following, so we assume now that this three-dimensional manifold is actually the unit tangent bundle to a surface. So let M be the unit tangent bundle of a compact surface, which of course was exactly the thing we were drawing pictures of before. It's where the geodesic flow took place. Let's let k of n equals 1 to infinity, be the closed geodesics, the closed orbits for the geodesic flow. So if we think of our unit tangent bundle as being a three-dimensional blob, then we have lots of closed orbits because it's an Anosov flow, like that. And then we can ask the same question. We stop at some stage, and we take out a finite number of orbits, and we ask how all the other orbits lie in the manifold relative to the first guys. And the way we ask it is using this kind of funny equidistribution result. And of course, the answer is that it holds in this case. Then the sequence in the set is equidistributed, distributed in the sense of Mesa. And there are other results which are rather similar, but this is kind of a simple one to state.
That's for constant curvature? Or?
It works in variable curvature. So for it basically it works simply if you know that the flow is an example of an Anosov flow. So either way around. The only way I know how to prove it works in both cases, constant and variable. So I don't know a different proof for constant. And the final comment is that the proof, the reason he was asking me was that the proof uses an old result. An old result of mine with Parry, which was proved using L functions, or dynamical L functions. And the old technique of dynamical L functions for Anosov flows. Okay, so it fitted onto two boards, which is not so bad. Okay, so this was just a simple application of the same circle of ideas. So the proof of the result, which is behind this, is just the same sort of machinery. It's you look at closed orbits, you look at maybe their lengths or some property of them. You define an L function. An L function is the same as a zeta function, except instead of just taking the products of involving lengths, you also encode some information like a character for each point. And then the analysis of the domain of that zeta function plus some classical number theory stuff, Tiberium theory, converts the complex analysis into asymptotic formulae. And that's how you can get sharper results in equidistribution. You can get counting arguments if you put lengths in. But it's the backbone of this particular proof. Anyway, so I wanted to finish on something which was a bit self-contained and distinct from not giving a very good account of the proof of the previous theorems. And I think that's probably the best place to stop. Thank you very much.